Hi, it's Moser with an introduction to limiting and excess reactants. More stoichiometry. So, by the time this video is over, you should be able to explain what limiting and excess reactants are and describe the effect that limiting reactants have on a chemical reaction. What you'll need to know going in is, number one, the difference between reactants and products, and how to write a balanced chemical equation. Okay, enough of that. Let's talk about cookies. Yay, cookies! Let's say you've set out to make cookies and you've got your recipe ready. Your recipe calls for 3 eggs, 1 stick of butter, 3 cups of flour, tablespoon of baking powder, teaspoon of salt, teaspoon of vanilla, and a cup of chocolate chips. Awesome! Cookies! Now, when you go to the cupboard and the fridge, what you discover is that instead of the 3 cups of flour you're going to need, in fact, you only have 2 cups of flour left. Can you make a full batch of cookies? No, you're going to run out of flour. You've got enough eggs, you've got enough butter, you've got enough of everything else. Heck, you got 2 bags of chocolate chips. But you don't have enough flour, which means that the amount of flour you have is really going to limit the number of cookies you can make. Oh, okay. In the Chapter 9, What Do You Know? Over the years, to the question, what stops a chemical reaction from occurring, a number of students, a small number, but a number, have said, maybe when something runs out. That's exactly it. So that thing that runs out is your limiting reactant. The limiting reactant is the reactant in a reaction that runs out and therefore limits the amount of other reactants that can combine, and because of that, limits the amount of product you can form. Sometimes you'll hear this called the limiting reagent. In the case of our chocolate chip cookies, flour is your limiting reactant because that's what's going to run out first, and it's going to control how many of the other ingredients you can use, and it's going to control how many cookies you can make. Let's take a very simple example using the synthesis of sodium chloride from sodium and chlorine gas. You saw a video on this. So we've got a balanced chemical equation. 2 moles of sodium plus 1 mole of chlorine, which is diatomic, yields 2 moles of sodium chloride. Well, if I have 4 moles of sodium and 1 mole of chlorine, you can see intuitively, without doing any math, that I'm not going to use up all of that sodium. We'll do the heavy math later, but let's just talk about this conceptually. We know that for every 2 moles of sodium that reacts, we can fully react 1 mole of chlorine. Well, if we have 4 moles of sodium, that means we should be able to react 2 moles of chlorine gas. But we're told that we only have 1 mole of chlorine gas. So the chlorine gas is going to run out, it's going to limit how much of the sodium can react, and it's going to limit how much of the product we can make. Let's take a single replacement reaction with iron 2 oxide and aluminum, which combine and form aluminum oxide and free iron. Now, just conceptually, we know that for every 3 moles of iron 2 oxide that react, we can fully react 2 moles of aluminum. Good. What if you're given 3 moles of iron 2 oxide and 5 moles of aluminum? Which one will limit the reaction? Ah, yes. You know, 3 moles of iron 2 oxide, because that 3 moles of iron 2 oxide can't react all 5 moles of aluminum. Okay, let's try another quick conceptual. What if we're given 4 moles of iron 2 oxide and only 1 mole of aluminum? Which one will be our limiting? Yeah, of course. The aluminum is now going to limit us because we only have 1 mole of it, so it cannot react all 4 moles of the iron 2 oxide. Are you seeing how this works conceptually? I want you to notice something. Because we are talking about limiting reactants, we're only talking about the reactants so far. As I said, we'll get to the heavier math in the next video, but I want you to realize that when you're talking about limiting reactants, you're always comparing reactants. You shouldn't hear a thing about products, not just yet. let's talk a little bit about where those excess reactants end up. So, I don't know if any of you have ever made soap, but I can tell you that if you're in my class, you'll get to make it in the next couple of weeks. Soap is the product of a chemical reaction between sodium hydroxide and a fat, any fat. And what you get is soap, which is actually an individual chemical with a chemical formula, and a product called glycerin. Okay, that's assuming that every single bit of sodium hydroxide reacts with every single bit of fat. Then these are the only things that you produce. Well, what if we have an excess reactant? We said in this case that the 1 mole of aluminum was our limiting reactant, which means obviously we're going to have extra iron oxide. Well, if our limiting gets used up, it runs out, and we have excess, where does the excess go? Well, the short answer is that it doesn't go anyplace. It stays right there in whatever vessel you've done your reaction in, and at the end, you have not only your products, but your excess reactant left over. It's just mixed in with the products. Well, that takes us back to our soap. So, sodium hydroxide is also known as lye, and it is a very powerful base. As a matter of fact, it's used as drain cleaner. It's caustic. It's nasty stuff. You really wouldn't want it on your skin. Fat, on the other hand, well, we put fat on our skin all the time. We're really just fatty water bags. The walls of our cells are made of phospholipids. And so we rub fat into our skin all winter in the form of creams and ointments and jellies. Great. So if you were going to make soap and you knew that you had to have either some excess sodium hydroxide floating around in your soap or some excess fat floating around in your soap, which would you pick? I'm really hoping you said fat. A soap bar with excess fat is a very nice moisturizing bar of soap. A soap bar with excess sodium hydroxide will burn the top layer of your face off. I suppose it might clear up your acne, but it really is the hard way to do it. So to summarize that, whatever reactant isn't fully used up is called the excess reactant. And, this is a very specific example, in soap making, we always calculate the amount of our reactants to allow for excess oil. Too much excess oil makes a soft bar, but a little bit makes a beautifully moisturizing bar. You certainly don't want to go the other way. So to recap, one of these reactants, unless we have absolutely nailed the calculations, is probably going to run out. Whichever one runs out is your limiting. When your reaction has run fully, there won't be any of your limiting floating around in there with your products. It's all gone. It's been used up. The other one, the reactant which has some leftovers, is your excess. And you'll often find traces, or more than traces, depending on how badly you've calculated things, of your excess sort of floating around in with the products. Depending on what your reactants are and what your product is, this can be okay, it can be a good thing, or it can actually be harmful. This is only part 1, but you should have a basic idea of what the limiting and excess reactants are, and be ready to take a brief conceptual recall quiz. Good luck!